Here we're going to learn about more chords and the distance away from the center that they have. So here you can see that I have two chords. I have chord AB and I have chord CD. And I can see that they are definitely an equal distance away from the center based on these segments here. These segments have the congruent piece there. So I know they are the same distance from the center. So the conclusion that I can make is that these chords are also equal. So what we're going to write is, if the chords are an equal distance or equal distant from the center, then the chords are congruent. So if EG is congruent to FG, then AB must be congruent to CD. And the same thing can be said backwards. For example, if the chords are congruent, then they must be an equal distance from the center. So if AB is congruent to CD, then GE must be congruent to GF. So now we can use that information to solve the problems at the bottom. So here I can see that I have some chords. I have these chords, and I can see that they are an equal distance from the center based on these segments here. They have the congruency there. And not only that, but they are perpendicular to the chords. So since these chords are equal distance, I know they're equal. Since they're being bisected by this perpendicular bisector, I know that this piece must equal this piece, which means this is also 6.5. So the total is 13. So that means the whole other side must also be 13. In this one here, there's a lot of different things that give away the answers. One of them is my linear pairs that I have here. And I know that these two have to also equal 180. So these are all 90. If these are all equal, these must be equal too. So then in that case, these are all 4. Since they're all 4, I'm going to use the Pythagorean theorem to solve for my hypotenuse, in this case, which is represented by the x. So that's just going to be 4 squared plus 4 squared equals x squared. 16 plus 16 equals x squared. 16 plus 16 is 32. So the last step to get x by itself would be to take the square root. And when you put that in the calculator, you're going to get 5.66 centimeters. Now, last but not least, we actually have to go dig in our toolbox and remember our rules for sine, cosine, and tangent. We have a couple different things here. So first of all, this arch, which is 90 degrees, is centered right here by this central angle. So if you remember from class, central angles are congruent to their arches. So if this arch is 90, this central angle that's coming from the center is also 90. What I also see here is a radius, or almost a radius. It's coming from the center, and it's creating a perpendicular bisector. So if this chord is bisected, well, so is the arch. So this arch must be equal to this one, which means that this angle is also equal there. And they're not just equal, but they're in half. So if this is 90, this whole thing is 90. Half of 90 is 45. So what I can make is this my theta. And if this is my theta and I label my triangle, I have my hypotenuse and x, which is the side I'm trying to solve for, that is my adjacent side. So I have a 90-degree angle and a 45-degree angle. Since it's a right triangle, I can use trig. Since I found out theta, which is 45, I can use that to label my triangle hypotenuse and adjacent. And that means that I'm going to use cosine. And cosine is the adjacent side over the hypotenuse. And since the adjacent side is the one that I'm looking for, I'm going to ignore that one, which means I'm left with multiplication. So I have cosine of 45 degrees times my hypotenuse, which is 12 square root of 2. When you put this all in the calculator, you're actually going to get just 12. So this problem, you had to dig back into your toolbox. You had to figure out which trig function you wanted to use. You also had to identify theta, which means you had to use what you knew about bisecting the angles, the central angle, and the arcs that they are intercepted by. And you had to put it all together.